All this is stoichiometry, okay? All related to like, how much of this do you need to get this much? Which one of these is limiting, and how much product will I get given these two ingredients? All this is stoichiometry. So learning goes, balanced chemical reactions. That's the first thing. I don't spend a lot of time teaching it. It's kind of boring to teach. It's boring to sit there and listen to. It just takes practice. Kind of like naming. I won't beat you over the head with balancing. I think you had some on the, did you have some on the quiz, some balancing? Kind of keep it basic. It'll come with practice, you know, type thing. The more you do, the better you get. I'm no wizard at balancing. There's one or two kind of pieces of advice we'll give you, and that's about it. It just comes with practice, and it's trial and error. You sit there and you go, okay, let me play around with this number. Let me put a 2 here. That's what it is. Master the interpretation of chemical reactions to carry out necessary calculations. This is what I was just talking about. Which reactant is limiting? How much reactant is needed? How much product will form? All these types of questions. This is the heart of the chapter. When you ask chemical educators, which I'm not, I'm trained as a research scientist, but when you ask chemical educators, they'll tell you this is one of the topics that is most important in general chemistry, stoichiometry. Most will agree on that. It's one of the major things you need to take with you forward out of general chemistry. We'll use these concepts to some extent. They're a little bit different to determine empirical and molecular formulas, but it's the same thing. It's that ratio approach. It's just not a chemical reaction. And we'll determine percent yields. All right, so calculating the mass of a product from the mass of a reactant requires the mole ratio from a balanced chemical equation. Because remember, when I say to you something like this, this can be interpreted as one atom of carbon combines with one molecule of O2 to form one molecule of CO2. But because a mole is just like a dozen, you could say a dozen carbon combined with a dozen O2 to give you a dozen CO2. Or you could say a mole of carbon combines with a mole of O2 to give you a mole of CO2. It's the molar relationship and the number of particles that matters, not the mass. Who cares about the mass? Carbon weighs 12, oxygen weighs 16. If I say to you, does this need 1 gram of carbon combined with 1 gram of O2 to give you 1 gram of CO2? No, of course not. It's kind of like those Lego blocks again, right? Assuming the Lego blocks have different weights for the different colors, the weight means nothing. So if you're given a mass, you've got to convert it to moles. That's what the recipe is. It's a molar recipe. So that molar mass that we learned in chapter 2, you know, that's just that number up there in grams per mole, right? CO2, it's going to be 44. That's 16 for oxygen, and 12 for carbon, 44. That's the molar mass. Okay? Just add them up. It's just in grams per mole instead of atomic mass units if you were talking about a formula mass. All right. So I always tell my students, you know, I kind of have a little jingle. If somebody give me a drum beat. Mass of A to moles of A, moles of A to moles of B, moles of B to mass of B. Okay, that's what it is. And A and B can be anything. It could be a reactant, it could be a product. So if you're given A, it's mass of A to moles of A, moles of A to moles of B, moles of B to mass of B. This is the stoichiometric relationship right here. That's from the reaction. That is the one-to-one relationship. This here is just your molar mass. Okay, so if I'm going to go from, I'm going to say, how much carbon dioxide can I form from 55 grams of carbon and unlimited oxygen in the air? Well, I'll say 55 grams of carbon converted to moles of carbon using the molar mass. Then I'll go from moles of A to moles of B and say, okay, well, 1 CO2 forms for every 1 mole of, that's my recipe, right? And then I can say, okay, well, the question asks for mass of CO2, so now I can use the molar mass of CO2 and convert it back to mass. That's the heart of a lot of this chapter. Important for the carbon cycle, you know, the carbon cycle, you learn this, I don't know when you learn it, but you should, I hope I never did my notifications. You guys see all my news alerts. I don't know, maybe you get it. Well, maybe you don't do that. You do carbon, you learn this like high school? It's not really. Maybe you took like a earth science class, environmental science type course, you might cover something like this, some of the element cycles. Anyway, we all should be familiar with photosynthesis. You certainly learn that. Combustion, most of you are probably in biology now too, right? Biology 1 and 2, maybe you're taking. Photosynthesis, combustion. Most of the carbon, a lot of people don't realize this, most of the carbon circling in the earth is contained in the carbonate sediments. That's where most of it is. And you got things like calcium carbonate. These are huge deposits of sediments that have collected over geological time. The amount of CO2 in the atmosphere is minuscule. Fossil fuels, the next big one. Those are, pockets of rich, broken down carbon compounds that were once living, that are millions of years in the making, right? Talking about when the dinosaurs roamed. That's when this stuff first started forming. Okay. Fossil fuels are basically partially broken down organic materials. They got trapped underground with limited oxygen. And that's why they stopped breaking down. Okay. If I take a bologna sandwich and stick it on a counter, come back and I don't know why I chose bologna. And I come back in a million years, I think it's going to be gone, right? There'll be mineral deposits left from what was in the bread and the meat, right? Everything's going to be broken down by the bacteria. But if I take that bologna sandwich and bury it underground where there's very little oxygen, you come back in a million years, you'll probably be able to detect something, just like a landfill. Some people are, digging up landfills and they see newspapers from the 1930s. They're so slow to break down because there's no oxygen. Okay, oxygen is key to aerobic degradation. It moves much faster and breaks down more completely than anaerobic. When I say anaerobic, I mean no oxygen. The bacteria, there's no oxygen, so you have to use anaerobic bacteria, different group of bacteria, different things happen. That's what happened here. Whether it be coal or petroleum, they are slightly different. They got trapped, and now we can dig it up. It's still got a bunch of carbon there, right? With bonded to hydrogen and stuff like that. We use it as a fuel. Of course, so photosynthesis and respiration are just basically the flip of each other, right? The exact opposite reactions. Plants take the CO2, right, and produce oxygen, right? And we do the opposite. We use up the oxygen and exhale CO2. So the left side are always your reactants. This means, gas, liquid. Aqueous means dissolved in water. These numbers out here cannot be changed. Those are the chemical component. You can't balance an equation by changing numbers and going like this, because you now just changed it from oxygen gas to ozone, which is not what the product is. The product is oxygen, okay? That's the chemical reaction. We know that. You balance by putting numbers out front here. You can't change the compounds by putting different subscripts down. So when you look at a reaction like this, you say to yourself, well, this is balanced, right? 1 sulfur and 2 oxygens on the left. Give me 1 sulfur and 2 oxygens on the right. Nothing needs to be done here. This is just a table showing you the ratios and the masses and things like that. But probably a slide that I will delete in the future. New book, new sets of slides. Sometimes I include something and realize, nah, not worth it. All right. Steps to balance chemical equations. I don't really follow any steps. The only one that I tend to pay attention to is this. But of course, you've got to have a reaction written out, okay? And the products and everything need to be appropriate to whatever the reaction is. If someone says, and I got examples built into the lecture, but if someone says, we burn methane and oxygen, write the balanced equation for that, you have to know that CO2 and water are the byproducts. And that's something we'll learn as we go along. You write the appropriate products, then you go about balancing. So you have to have that balanced equation there. And this is the good advice I like. This is something I do. Choose an element that appears in only one reactant and one product, if that exists, not always the case. to do first. It just simplifies things. You'll find that out. We typically save like oxygen to the end because that's kind of appears typically in multiple places. You release sulfur. Why is this? And you release sulfur. This sulfur dioxide goes to form sulfur trioxide in the atmosphere, and then this reacts further to ultimately give you H2SO4. Does anybody know what H2SO4 is? Have you worked with it in lab? What is it? Sulfuric acid, right? So you're forming sulfuric acid in your atmosphere, and then it's raining down on us. Okay? It doesn't hurt people, but it kills trees, acidifies lakes, affects aquatic systems, all of this. So sulfur in coal is a big problem, and coal in general is a dirty fuel that has seen better days and needs to become part of our past. Regardless of jobs, we always have to transition away from poor technologies. We just have to do a good job of making sure the people that are in that industry are taken care of. But coal has no business being part of our future energy. All right, so this is not balanced, right? So we've got to do something because this is the chemical reaction that happens. That's all it's saying. It's not balanced. It's just saying when sulfur dioxide reacts with oxygen, we get SO3. Okay? Now, if I had one sulfur dioxide molecule and one oxygen molecule, this reaction couldn't possibly happen, correct? There's no way for it to happen. The only way that would be, I'd have to go, I'd get SO3 plus an extra oxygen, right? That's not what happens. It doesn't happen. Okay? So that reaction will not occur if you had a single molecule of each. That's why we tend to think of these on molar scales. Okay? And then one will limit how much SO3 forms, and you'll have leftover of some of the other one, right? That's all. You can't look at this on a basis like that. Reaction will not occur if you're looking at individual molecules and atoms. So it's easy enough to balance by putting a 2 all the way on the right and all the way on the left. We wind up with 6 oxygen on the right and 6 oxygen on the left. And of course, when you multiply these, it's 2 times the 2 here. You have 2 oxygen there, so you want to have 4 oxygen there. Plus the 2 there, 6. So now it's balanced. So effectively, that's another way of saying you have to have at least 2 molecules of SO2, 1 molecule of oxygen to form 2 molecules of SO3. Better just think about it in terms of moles. But, okay, question. Combustion reactions are a really important class of compounds, class of reactions. So this is the simplest one. If you have pure carbon, like I wrote before, reacting with oxygen, you get CO2. It's rare we have pure carbon. But coal is almost pure carbon. It's got a bunch of hydrogen there too. It's got some other stuff. But you can say, diamond is pure carbon. But diamond doesn't react because of the structure of it. But anyway, pure carbon plus oxygen gives you CO2. This is just showing you that mass-mole relationship. This is the molar mass of carbon, the molar mass of oxygen, and the molar mass of CO2. So, to calculate the mass of CO2 produced by the combustion of 1.01 times 10 to the 13 kilograms of carbon, that number has significance. I don't know if it's the amount of CO2 we're putting into the atmosphere or something like that. Anyway, It's in here somewhere. So, the significance of that number is why they chose that number. Count the mass of CO2 produced by the combustion of 1.1 to 10 to 13 kilograms of carbon. Well, you must start with the mass of carbon. So this is the mass of A to moles of A, moles of A to moles of B, moles of B to mass of B. That's what we're doing here. There's the mass of carbon. I didn't do it, they did it. This is from the book, but we just need to convert that to grams because molar masses are always in grams. Now, straight from the periodic table, that 12.01 grams there. So that gives me the moles of carbon. Look at your units. Kilograms of carbon, grams of carbon, grams of carbon. Dimensional analysis. Move across, go from mass of carbon, kilograms of carbon, to grams of carbon to moles of carbon. Moving across, dimensional analysis. That's how many moles of carbon we have. Now we're going to do moles of A to moles of B. That number is just coming down here. I'm looking at my stoichiometry and saying 1 mole of CO2 for every 1 mole of carbon. Boom. That's moles of A to moles of B. It gives me moles of CO2. Then I'm going to do moles of B to mass of B. I'm taking this number here. Whoops. There it is there. Oh, this is figuring out the molar mass of CO2. We've already talked about that. I told you what it was, 44. So here it is, moles of CO2. Going to convert it to grams, and they want the answer in kilograms. So one last step to get to that. Here it is, kind of in one step down here. That's all. That is kilograms of A to grams of A, grams of A to moles of A, moles of A to moles of B, moles of B to grams of B, grams of B to kilograms of B. That's your answer. Dimensional analysis. Just moving across, using your molar masses. Boom, 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 boom. Questions?
I just have one. On the very last one where it's all together, where it says 1 mole of CO2 over 1 mole of CO2, is that supposed to be just 1 mole of carbon?
Oh, that's a mistake. Yeah. Yep. 1 mole of CO2, very good eye. For every 1 mole of carbon. Very good. Lots of mistakes and then new additions that always happens. Found a bunch, a couple in the text and a bunch in their banks, their test banks, and things like that. So let's do a practice here. How much carbon dioxide would be formed if 10 grams of propane, that's propane, 3 carbons, were completely burned in oxygen? So this would be like you grilling if you use propane rather than charcoal. How much carbon dioxide would be formed if 10 grams of C3H8 were completely burned in oxygen? Now, this is a combustion reaction. You need to know something before we can go forward. And that is, there's always 2 products of a combustion reaction. What are they? Carbon dioxide and water. That is it. That's a complete combustion. Of course, things go wrong and you have some propane left over and you have some other carbon compounds produced. But ideally, always, carbon dioxide and water are the 2 byproducts of combustion reactions. So now, and we know we need to burn it in oxygen, right? We can write a reaction and say C3H8 plus O2 gives me CO2 plus H2O. Okay, so now we have to balance it. Now the carbon's only in one place, so why don't we just put a 3 out in front of the here. And of course we need 8 hydrogens, so I put a 4 here. That gives me 10, right? Oxygen. You agree? Put a 5 here. Now, what if the number on the right gave me an odd number of oxygen? Say instead of 10, it was 11 oxygen. What do you do? Your book talks about this. Yeah. So what we can do is, Andrew, right? Said everything multiplied by 2. Is that what you said? Yes. But first you've got to do, so let's just say for chance, we wound up with 11 oxygen on the right. So we could just do 11 halves over here because it's 11 divided by 2 times 2, right? Everybody see that? It's 11 halves, but you got a 2 here. So it's going to be 11, right? But you've got to multiply by everything by 2 because a lot of times people don't like fractional coefficients. So that's what Andrew's saying. Multiply everything by 2, you wind up with 2, 11, 6, and 8. You see? No, you don't. I can tell. So you got an odd number on the right. So it was easy before. We had 10 oxygens total. So we put a 5 out here. 5 times 2 is 10. Now the oxygen's balanced, right? But if I wind up with an odd number like 11 oxygens, well, you can't put a number out in front, a whole number out in front. So you put 11 halves because 11 halves times 2 is 11, right? And you can leave it like that, but sometimes they don't want you to leave it like that. Smart work. And a lot of people don't want fractional coefficients. So to get rid of the fraction, you simply multiply everything through by 2. That's all you do. So it becomes 2, 11, 6, and 10 instead of leaving it as 11 halves. Does that make sense? There's something in the textbook. There wasn't one on their quiz, was there, that I asked like that? I don't think so. But there is, I remember seeing it, smart work in the textbook or both, okay? So that's how you handle those if they're off. Back to our question, which we're good with just the 5 out front. Right? We're balanced. Okay. How much carbon dioxide? Oh, I'm going to do this right off the bat so I don't forget what I'm asked. How much carbon dioxide would be formed if 10 grams of C3HD were completely burned in O2? We say completely burned in O2, that means we've basically got unlimited O2. We don't have to worry about it, okay? So what do I do here? How do I answer this question? Mass to moles, moles to moles. And then I said how much, we'll put it in grams in the end. So we'll go back to mass. How much, let's say in grams. So who said that? Houston? Was that you? So it was 10 grams times the molar mass, 12 times 3, 36 plus 8. Oh, it's 44 also. That's just coincidence, the same as carbon dioxide. Roughly 44 grams per mole. We want that in the denominator because we want to get rid of grams. I've got that's mass of A to moles of A, right? And my A here is propane. Then I do my molar relationship. I say 3 moles of CO2 for every 1 mole C3H8, and then times 44 grams of CO2 for every 1 mole. You can see we're multiplying by 44 and dividing by 44. So really the answer is just 30 times 3, right? The answer is going to be 30 grams. Did I see that? I really should be using 3 sig figs. 29.9, thank you. I only took 2 sig figs here, you know, I got sloppy. Anyway, you get the idea. We were given 3 sig figs, so I should have took 3 sig figs in my molar masses. And then the number of moles, that's exact, so that's not 1 sig fig. These are exact numbers. Exactly 3 moles for every 1 mole. Questions? Mass of A to moles of A, moles of A to moles of B, moles of B to mass of B. Good. Now, sometimes something is limiting. And what you have to realize is that, and this is the one, is this the one? Heck, I like the other example, but anyway, this is the one that doesn't do it right. It's not always the one that's less that's limited. It's the one that's less based on the recipe. Go back to my 5.5 cups of flour and 1.25 cups of water, right? If I told you I had, and that forms 2 pizzas, I told you I had 4 cups of flour and 1.25 cups of water, what's limiting? The flour, even though there's more flour than water. It's limiting based on the recipe, right? That's what's important. You can't just look at the one that has less and say, oh, that's limiting. So here, we're supposed to have twice as much oxygen as methane, and we have 2 methane. We have 1, 2, 3, 4, 5. So we got plenty of oxygen, which means methane is limited, right? You see that? It should be a 2-to-1 ratio, but there's extra methane. I mean, there's extra oxygen. See, it should be two of these for every 1 of these. So here's we have 2 of these, which means we need 4 of these. 1, 2 for that one. And then 1, 2 for this one. We still have 1 left over. So the methane is limited. And that's easy to see. It's just pictorial and the numbers are easy. When you get calculations, lots of times it's going to be, the balance is going to be 5 to 2, and the masses are going to be 36.9 grams to 22 point. You're going to have to do the math. You're not going to be able to just look at it. This is the classic sandwich example. I like pizza better than sandwich. Well, actually, I love sandwiches. Not on that kind of bread. But anyway, you guys don't want to hear about my diet. All right. This is the classic example, though, because you can picture it. You've got 2 slices of bread, 1 slice of cheese, and 1 slice of salami. Make 1 sandwich. Which one of these is limiting based on the number of slices? You can look at this, but it's the classic example because it just shows it pictorially really nice. All right, substance that is completely consumed in the chemical reaction is the limiting one. It's also, this is the key point, whoops. It determines the amount of product that can be formed, right? So if I had the 4 cups of flour and the 1.25 cups of water, you're only making 1 pizza. And you got a bunch of flour left over, right? Water left over too, because you don't need all that water to make 1 pie. So you'll have both of them will be left over. All right. Yeah, you can only make 1 pie. It's not like a chemical reaction where we can use up that and make more molecules. You either make a whole pie, you can't make like a part of a pie. I guess you could. You could just figure out what that would result in numbers of pies. All right, so identified by number of moles of reactant, stoichiometry of the balanced chemical equations. That's what we're going to do. We're simply going to look at what we're given, look at the recipe, and how much we're given, and from that we should be able to determine which one's limiting. So, hydrogen fuel cells. These are great. This is what was part of our space shuttle. This is part of the technology that came out of the space race. And these are the cells that are in the shuttle. They're not what's powering the rocket. That's rocket fuel, not what's lifting it off. It's for like controlling instruments and stuff like that. It's part of the power of the shuttle. In fact, that's one of the problems that went wrong with Apollo 13. One of their fuel cells was messing up, among other things. Well, that's the one that didn't complete their mission, but they crashed back down, but they all survived. So there are. You look at that reaction. It says hydrogen fuel cells use the following reaction to generate. How the heck do you get electricity from making water? What the heck is that? So there's a whole big group class of reactions. One of the biggest classes around. And Combustion reactions fall under this. That's how big this classification of reactions are. Combustion reactions are part of this, and they're called oxidation reduction reactions. We'll get introduced to it in chapter 8, and we'll come back to it in chapter, I want to say 17 in the old edition, the very last chapter of Gen Chem 2. Tons of reactions in your body are oxidation reduction reactions. What that means is electrons are being transferred. Same principle as a battery. If electrons are going to be transferred from A to B in a chemical reaction, well, if I separate A and B in two different cells and connect them with a copper wire, I can now power something because the electrons have to move through the copper wire. I can power a light bulb and come back and go over to cell B. That's all you're doing with the battery. Fuel cells are the same idea. You're harnessing the electrons' movement and generating electricity. So this is a chemical reaction that electrons are being transferred. And we'll learn about that a little bit, like I said, in chapter 8. But we got to determining the limiting reactant. And in the old edition of the textbook, they showed two ways to do this. And one of my comments to the publisher when they were putting out the new edition was that I don't even bother teaching the other way anymore. It winds up just confusing students. I like to stick with one way that's straightforward. And in some cases, it involves an additional step, but you're much less likely to make a mistake and to get the wrong answer. And what we're going to do, and those of you that are really good with math and really see this and want to do it by looking at the ratios of reactants, go for it. Okay, this is the only way I'm going to teach it though. To determine the limiting reactant, we're simply going to calculate the amount of water that each of the two reactants would produce if the other one was considered unlimited. So I'm going to take my 0.055 grams of H2 and just assume I got plenty of oxygen to figure out how much water is produced, which is the product. And we're going to do the same thing we've always done: mass of A to moles of A, moles of A to moles of B, moles of B to mass of B. You can even stop. You don't even need mass. You can stop at moles if the only question is, let's see what the question is. You just ask which one's limiting. So you don't even need this last step. You can do it in terms of moles. But most of the cases, lots of times they want to know the mass of product formed. So that last step is going to be key. So all we've done is just do the calculation for each of the reactants, and whichever one produces less water is limited. Now you can tell they're supposed to be in a 2-to-1 relationship. So you can just look at that and know, right, that the hydrogen's limited. No, you can't. Never mind, because that would be mass. You'd be looking at mass. You can't do that. You've got to convert it to moles. In some cases, you can tell because the molar masses are very different here. One of them's 32 and one's 2. So whatever the answer is here, you'd have to compare those two. The product, and teaching was to just, look at the molar relationship of these two and say, okay, it's supposed to be 2-to-1. Is this 2-to-1? No, it's 2.5-to-1. So that means this one's limiting, or it's 1.5-to-1. That means this one's limiting. To me, it's a little bit trickier. This is foolproof. Calculate how much product, whichever number's less, that's your limiting. Does that make sense? Calculate your product for both, choose the lower number. So in this case, does it say it up there? That H2 is limiting. Since there it is. Since hydrogen produces a smaller mass of water, it is the limiting reactant in this reaction. Since it's the limiting one, here's the next step. It determines how much is formed. If it determines how much is formed, which is this right here, that's your answer. If the question says how much water formed, right? It's got to be based on the limiting one. And then if hydrogen is limiting, oxygen must be in excess. So how do we figure out how much oxygen is left over? Well, just do the same thing. Mass of A to moles of A, moles of A to moles of B, only this time A and B are going to be both reactants. And you're going to say, okay, I've used up all 0.55 grams of hydrogen, because that was limiting. Convert it to moles, mass of A to moles of A. 1 mole of O2 for every 2 moles of hydrogen. That's coming from here, right? Same thing. My A and B have just changed, but it's still mass of A to moles of A, moles of A to moles of B, moles of B to mass of B. So that's how much oxygen was used. We started with 0.48. That's what's left over. Questions? Digesting that? See what we did? So your A and B can be anything you want it to be. Every question you ask, product, how much reactants left over, any of that. So all we did was we said mass of A to moles of A. In this case, we're looking at the relationship of the two reactants because we want to know how much of the one that's in excess is left over. Okay. Theoretical yield. All right. That was later, it's like 10:30. In the reaction of 0.055 grams of hydrogen, 0.48 grams of oxygen, is that the starting amounts? Yeah. We previously determined that H2 is a limiting reactant because the smaller mass of water was produced. The previous calculations also allow us to determine the theoretical yield of the reaction. 0.49 grams is what we should get. Everything goes perfectly. Okay? This is the maximum amount of product that could be obtained from the given quantities of reactants. 0.49 grams of O2, it's just showing it again. The same thing that was right here. Or that, no, right here. Same thing right there. 0.49. That's just repeated. Okay? That is the theoretical yield. On paper, what we should get if everything goes perfectly, which of course never happens. If 10 grams of methane is burned in 20 grams of oxygen to produce carbon dioxide and water, what is the limiting reactant? How many grams of water will be produced? So we'll do example. We'll get into percent yield later. I'm introduce theoretical yield. So this is still a theoretical yield calculation. Theoretically, how much should occur here? Okay, so we've got methane is burned in oxygen. We know this, even if it wasn't told to us. We can simply put a 2 out in front here, right? That gives me 4 hydrogen balanced, and then we just need a 2 out in front of here, and we're balanced with 4 oxygen on both sides, 4 hydrogens on both sides, and 1 carbon on both sides. We got 10 grams of methane, 20 grams of oxygen. Okay. And the question is, what's limiting and how many grams of water will be produced? So let's take this and do it. So we've got 10.0 grams of CH4, that's mass of A, times, and I'm going to get sloppy with my sig figs and molar mass because I know methane is about 16, so I'm just going to do 16 grams in 1 mole, times, I need my balanced equation here. And what do we ask for? We're asked for water. So now let me point this out too. You can do this for CO2 or water. It's the same, just a different massing out. But the question's asking about water. So obviously we're going to do water. We're going to ignore CO2. But you could calculate how much CO2 would be produced also, right? But we want to use water here. And the relationship is 1 methane and 2 waters. So times, and we want to go to water. So 2 moles of H2O for every 1 mole CH4. And this is CH4 here, so we just don't get confused. And ultimately, what do we ask? How many grams of water? So I'm going to do the last step because they want grams, not moles, times 18 grams of H2O roughly for 1 mole of H2O, right? Looking at my units, make sure I didn't make a mistake. Grams of methane, moles of methane, moles of methane, moles of water, moles of water. I'll have grams of water as my answer. I'll need someone to do that calculation for me. I do not have this solved. And then while someone's calculating that out, we can do the 20 grams of O2 times 1 mole of O2 is 32 grams times the numerator will be the same, 2 moles of water, but the denominator for every 2 moles of O2, we need to use our stoichiometry, right? Our recipe, 2 moles of O2. So these two right here, these are our stoichiometry relationships. Times, and the last one's the same too. 18 grams of H2O for every 1 mole of H2O. Has anybody done any of the calculations? Top one maybe? 22.5 we get? Okay, thank you. 22.5 grams, and that's of H2O. 10.6. 10.6, that's clear winner for our limiting reactant. Because 10 is less than 22.5. So O2 is limiting. And we will get 10.6 grams of water for this reaction. And that's all we did. We calculated the product given the 2 starting amounts. Questions? We good? Now you can look at percent yield. So the actual yield is what I told you before we get in the lab. So the amount of product produced in a reaction, the actual yield is often less than the theoretical yield. So it's very simple. It's just like any percent, right? Part over the whole times 100. We don't need to spend a lot of time on this. This has to be given to you. Or sometimes you could be given the percent yield and be asked to calculate that. But that's what happens in the lab. So in fact, you guys are doing a lab. I don't know if you've done it yet. If I think magnesium oxide, not yet, okay? Yes, you start, okay, maybe, did you guys do a percent? Did you figure out how much yield you got? Okay, good. So you're familiar with this a little bit. You had this magnesium oxide, some of you might not have done it yet. Actually, I think everybody did that because that was pretty early, I think. And that's all it is. So now we got a nice, meaty problem. Because we've got a lot of stuff we have to be able to do here from scratch. And this is where your knowledge from the first couple chapters is important. Aluminum burns in bromine liquid, producing aluminum bromide. In one experiment, 6 grams of aluminum reacted with an excess of bromine to yield 50.3 grams of aluminum bromide. Calculate the theoretical and percent yields. We don't have to worry about limiting because we're told excess. Don't have to worry about limiting. Okay, we have to write the reaction and then balance it, right? So, a lot of knowledge here needs to go into this. Okay, aluminum. That's just elemental aluminum. There it is sitting on the periodic table, atomic number 13. Just going to be the aluminum metal, so aluminum solid. This is the tricky part. Plus, what do I put for bromine liquid? What? BR2, not BR, right? Because bromine is one of those diatoms. Remember, the halogens are diatoms. So if you just put BR, you're not going to get the right answer. It's the element bromine, which is a liquid at room temperature. BR2. Producing aluminum bromide. What's the formula for aluminum bromide? AlBr3, right? Because bromine's -1, aluminum's +3. AlBr3 okay. Balance it. What do we do? What is it? 2, 3, 2. So basically you've got that bromine, right? So you're just going to balance it by putting a 3 here to make 6. And then you balance the bromine here to make 6. And then Megan's exactly right. So then we wind up having a 2 here to balance the aluminum. So we get 2, 3, 2. So you've got to take knowledge from exam 1 and realize BR2 is, bromine is BR2. You also have to be able to write the aluminum bromide formula, knowing that bromine's -1 and aluminum's +3. And then you got to balance it. You're learning in this chapter. Now we have to do the calculations of the stoichiometry. Okay, so I think I had a whole nother page open for this. Here it is here. Should have wrote it there, but anyway. So we've got 2 aluminum plus 3 Br gives me 2 AlBr3. 6 grams of aluminum. Excess, we don't have to worry about this, infinity amount. 6 grams of aluminum react with excess bromine to yield 50.3 grams of aluminum bromide. I've given you the formula mass for aluminum bromide, so we don't have to spend time calculating that out. What do I do? Mass to moles, but of what? What am I doing? Aluminum, right? You take the aluminum and 6 grams and figure out how much aluminum bromide should form. The 50.3 is what the actual yield is. That's what this is. Not what you get on paper. That's the actual yield. The theoretical yield is what Houston's telling us to do is 6.0 grams of aluminum times, what's aluminum, like 26.98. 26.98 grams in 1 mole times 2 moles of aluminum bromide for every 2 moles of aluminum. 6 grams of aluminum reacted with excess bromine to yield 50.3 grams of aluminum bromide. Question says, calculate the theoretical percent yields. Excess bromine, okay, we're good. We're going to want the mass times, and that's why you've already got it, 266.694 grams per mole. And I'll need someone to calculate this out for me. Skip the third one, it's just times 2 multiplied by 2. So it's 6 divided by 26.98 times 266.694. What? 59.3? 59.3 with confirmation. So that's our theoretical yield, what we should get on paper that you calculated from stoichiometry and molar masses. What we got is 50.3, so we can easily do the percent yield. And what do we get? It's a good yield. 84.8%. That's our answer. Questions? Good. Percent composition, I'm going to glaze over because it's really easy. This is just the amount within a substance rather than a chemical reaction. You know, something like iron oxide, I should say iron 2 oxide on FE2, I mean FeO. Anyway, so we can look at the percentage of total mass, and that's just a. That's just the mass of iron over the total mass of iron oxide times 100. That's all it is, percent composition. So if you ask for the percent of carbon in methane, you just say 12 divided by 16 times 100. And obviously those two percentages should have to add up to 100. So theoretically, after you get this one, you can just do 100 minus that, or you can do the calculation like this. That's your call. Assuming you didn't make a mistake on the first one, the second one's a nice check to make sure they add up to 100. Because if you make a mistake here and then you do the 100 minus, it won't catch your mistake. But if you do this one and then do this one and check and make sure they add up to 100 and they don't, then you catch your mistake. That's percent composition in a nutshell. It's needed for empirical formulas. That's why we need to introduce it. So empirical formula is doing this same type of thing here, with no chemical reaction, but the same molar relationship that we used in chemical reactions we can use. Because what this is a molar relationship. There's 1 mole of iron for every 1 mole of iron FeO. And there's 1 mole of oxygen for every 1 mole of FeO. Okay? So when I say something like CO2, there's 2 moles of oxygen atoms for every 1 mole of carbon dioxide, right? This can be communicated on a molar relationship. That's what this is. Because atoms, Avogadro's number, atoms, numbers of molecules in moles can be equated, not mass. That's what Avogadro's number tells us. So, an empirical formula is the smallest whole number ratio of elements in a compound. So, this here is a molecular formula, but it's also an empirical formula because you can't reduce it any smaller, right? Where this is a molecular formula, but not an empirical formula. That is glucose, okay? Simple sugar, the simplest of sugars. So the empirical formula for that would be CH2O, right? Because you can divide them all by 2. So empirical formula is that lowest ratio. Okay, and of course for ionic compounds, we never had anything but an empirical formula, right? This is an empirical formula because there are no molecules. There's no molecular formula when you have metals and non-metals, remember? So that's always been an empirical formula. All right, so what we're going to do is convert all of these masses to moles and look at this relationship. So I'm trying to remember what my my little jingle for this one is. I don't have it written down here. I think. It is, oh yes. Percent to mass, mass to moles, divide by smallest, multiply to a whole. Percent to mass, mass to moles, divide by smallest, multiply to a whole. So if we're told a percentage, we're just going to assume 100-gram sample. So if you're told, so what we do sometimes is we can take a sample. It's 32% oxygen and this much hydrogen, okay? But we can't tell you the formula. It requires another instrument. Now it's pretty easy to do nowadays, but anyway, you get the idea that sometimes you might have the percents, but not know the actual formula. So this is what this allows you to do. We do this a lot with combustion analysis. And you'll see that, I think, in your book. I might even do an example on Thursday. So that's what this slide is telling you. I'm just gonna let you look at this on your own time. I think I'd rather just do the example. Empirical formula may or may not represent the number of atoms in the molecular formula. This is what I just said with the glucose, right? The molecular formula is a multiple of the empirical formula right here, right? Multiple of 6, okay? So sometimes we can get to this, but we can't actually get to the molecular formula. And sometimes we can get the percentage of things, but we need to determine the empirical formula. So there it is, assume 100-gram sample. Once you have the percentages, that's my percent to mass. It doesn't matter if I have 100 gram, 1 gram, or 1,000 gram, right? It's still FeO. So the percentages will be the same. And hopefully you see that, right? The percentages will always be the same. It doesn't matter the amount of my sample. So there's going to be a certain percentage of hydrogen in water. It doesn't matter if I have a liter of water or a gallon of water, right? So the easiest thing to do is assume 100-gram sample. Your percentages then become masses, right? So now we have 69.94 grams of iron and 30.6 grams. That's the percent to mass, mass to moles, divide by the smallest. You take the smallest of the moles and divide each of them by that. So this becomes 1. So this is called normalizing. You want everything compared to 1. Okay? This is the mathematical way of determining it. We get it on a ratio of 1. And now we know there's 1 mole, for every 1 mole of iron, there's 1.5 moles of oxygen. Now, of course, we can't write our formula as FeO 1.5. So the last step is to multiply to a whole. And you look at those and you say, okay, how do I multiply 1.5 to get a whole number? Multiply by 2, right? If I multiply that by 2, I have to multiply the iron by 2. I'm changing the ratio. It's just like my recipe. I can't double my flour and leave my water the same. So I'm going to multiply this by 2. Well, my pen stopped working. There it is. By 2, I have to multiply this by 2. So we wind up with Fe2O3 based on the percentages that were given us. Again, what did we do? We took the percent, we assume 100-gram sample, we go from percent to mass, mass to moles. That's the same as always. We always go mass to moles. This is new. We're dividing by the smallest. So looking at trying to get the ratio. Okay, that's all we're doing. We're getting the ratio based on 1, and then we can pick a number that allows us to multiply everything to get it all whole numbers. And this is an empirical formula. Questions? Still got combustion analysis left and a empirical formula example. Combustion analysis quite a bit. So we're going to do this example, and that's what we'll end with. Okay. This is chalcocite, a particular mineral, highly prized source of copper. Its chemical composition is 79.85% copper, 20.15% sulfur. What is its empirical formula? So we're going to end the day by just doing this calculation and determining the empirical formula. We're going to follow my little rule or jingle, whatever you want to call it. Percent to mass, mass to moles, divide by smallest, multiply to a whole. So we'll just assume 100-gram sample, right? So we're going to have 79. And then we'll do sulfur, 20.15 grams times grams of sulfur times 32.065. I should warn you here that empirical formulas are particularly picky. And that is, you don't want to shortchange yourself on sig figs. Meaning, we have 4 sig figs here. You notice I've taken 5 sig figs in my molar masses. Take as at least as many as you're giving, because I've seen good students do all the work right and not be able to get the empirical formula because they rounded their numbers too much. And in the end, they wind up with like a number like 1.41. And what do you multiply that by to get a whole number? You're never going to see anything like that. They're always going to be obvious. They're going to be 1.5. So you multiply by 2. 1.333. So you multiply by 3. Right? 1.25. A quarter, right? Multiply by 4. They're always going to be like that. If you get a weird one, you've done your math wrong. Okay? So make sure. Now, I do need answers to these. What is it?
1.2
for the first one? 6.6?
Yeah.
Okay, that's moles, right? Someone else, the second one? 0.6284, right? Okay, that's percent to mass, mass to moles, divide by smallest. So what I'm going to do now is I'm going to take that smallest one and divide this by it. And that obviously is equal to 1. And take this one. And obviously, I don't need you to do the math for the bottom one, but the top one looks like it's going to be darn close to 2. Is it? Did you get like 2 what? Okay. Approximately 2. When you get something like that, that's close enough. If you thought I had it in my comments or notes what the formula was to make sure we did it right, but that looks pretty straightforward and easy. Questions? Percent to mass, mass to moles, divide by smallest, and if necessary, multiply to a whole. We good? All right, good place to stop.